Hello, everyone, and welcome to Chapter 8, Section 1. We're starting a new chapter, and here we are in Section 1 on molecular compounds. A lot of the labs this week will be talking about compounds and bonding, so you'll get a lot of opportunities to practice this material, both in lab and in your discussions and quizzes and so forth. All right, so let's get started here. Molecules and molecular compounds. In nature, only the noble gas elements such as helium and neon exist as uncombined atoms. And that is because they are monoatomic, and that is they consist of single atoms. Helium, which is less dense than air, is often used to inflate balloons, as you know. But not all elements are monoatomic. For example, oxygen, O2, represents two oxygen atoms that are bonding together. And scuba divers, for example, will breathe compressed air, which is a mixture that contains oxygen gas. Ionic compounds are generally crystalline solids with very high melting points, as we learned in Chapter 7. Other compounds, however, have very different properties. Water, for example, H2O is a liquid at room temperature. Carbon dioxide, CO2, and nitric oxide, N2O, are both gases at room temperature. So everything is a little different. The attractions that hold together the atoms in oxygen, water, carbon dioxide, nitrous oxide cannot be explained by ionic bonding, which we talked about in Chapter 7. These bonds do not involve the transfer of electrons. So how do these molecules stay together? We'll talk about sharing electrons. Recall that ionic bonds form when combining atoms will give up or accept electrons. Another way that atoms can combine is by sharing electrons, and that's what we're going to focus on with these molecules. Atoms that are held together by the sharing of electrons are joined by what we call a covalent bond. A molecule is a neutral group of atoms joined together by these covalent bonds, which are formed when we share electrons between those atoms. Oxygen gas consists of oxygen molecules, where each oxygen molecule consists of two covalently bonded oxygen atoms right there. Those are the two covalently bonded oxygen atoms. An oxygen molecule is an example of a diatomic molecule. Di means two, so this is a molecule that contains two atoms. And you can see other examples of diatomic molecules here. We have hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These are diatomic molecules, a molecule that contains two atoms. Other elements found in nature in the form of diatomic molecules are examples that are shown there as well. Molecules can also be made of atoms of different elements. For example, water. A compound composed of molecules is called a molecular compound. So here is a water molecule made of two hydrogens and an oxygen. And because of the molecular arrangement, water has a little bit of an angle to it, the actual molecule. So water is an example of one of those molecular compounds. A molecular formula is the chemical formula of a molecular compound. And a molecular formula will show us how many atoms of each element a substance contains. So for example, glucose is made up of 6 carbons, 12 hydrogens, and 6 oxygens. So we write the molecular formula of glucose as C6H12O6. Butane is made up of 4 carbons and 10 hydrogens, and octane is made up of 8 carbons and 18 hydrogens. So those molecular formulas are telling us how much of each atom are in that particular molecule. The molecular formula of water is H2O, and notice that the subscript written after the element symbol indicates the number of atoms of each element in that molecule. If there's only one atom, for example, in H2O, the subscript 1 will just be omitted. So if you don't see a number after the letter, then you will just assume that there's just one of the atoms present in that molecular formula. The molecular formula for butane is C4H10, and according to this formula, one molecule of butane will contain 4 carbon atoms and 10 hydrogen atoms, as shown there. A molecular formula will reflect the actual number of atoms in each molecule. The subscripts are not necessarily the lowest whole number ratios. Note that the molecular formulas will also describe molecules consisting of atoms in one element. So for example, an oxygen molecule will consist of 2 oxygen atoms bonded together, and its molecular formula will be O2. A molecular formula does not tell you about the molecule structure. So for example, the molecular formula does not show either the arrangement of the various atoms in space or which atoms are covalently bonded to one another. A variety of diagrams and molecular models can be used to show the arrangement of atoms in a molecule. And we see that here. We see the space-filling molecular model of ammonia, which is made up of 1 nitrogen and 3 hydrogens. We see the structural formula, the space-filling formula, the perspective drawing, which uses arrows that either point to the center or away from the center to show where in 3D space these molecules will be coming out of, and then the ball and stick molecular model. So lots of different diagrams can be used to show the arrangement of those atoms in a molecule. And as we go through this, the next couple chapters, we'll see those different arrangements. The arrangements of atoms within a molecule is called its molecular structure. And the molecular structure of carbon dioxide, for example, shows how the 3 atoms are arranged in a row. It also shows how the carbon atom in each molecule is in the middle between the 2 oxygen atoms. So one molecule of carbon dioxide contains 2 oxygen atoms and 1 carbon atom. The carbon atom is in the middle, and the oxygen atoms are on each side. And due to the electron configuration and arrangement, it will be a very linear or straight across molecule. The arrangement of atoms within a molecule is called its molecular structure. The molecular structure of water shows how oxygen is in the middle between the 2 hydrogen atoms. So here's your oxygen, and you have the 2 hydrogen atoms. Water is not linear like carbon dioxide. They are not arranged in a row. Instead, the hydrogen atoms are mainly on one side of the water molecule, where the oxygen is on the other side. And that's due to the electric charge. And we'll talk about that in a little bit too. The molecular structure of ethanol is a little more complicated. It has 2 carbons, 6 hydrogens, and 1 oxygen. And each carbon is bonded to 4 atoms. Each hydrogen is bonded to 1 atom, and the 1 oxygen is bonded to 2 atoms. So here we have the 1 oxygen, we have the 6 hydrogens are in white, and then the 2 carbon atoms are in black. So we kind of have a little bit more interesting molecular structure of ethanol. The representative unit of a molecular compound is a molecule, and for ionic compounds, the smallest representative unit is the formula unit that we talked about in chapter 7. And recall that a formula unit is the lowest whole number ratio of ions in an ionic compound. It is important not to confuse formula units with molecules. So a molecule is made up of 2 or more atoms that act as a unit. No such discrete units exist in an ionic compound, which consists of a continuous array of ions. And there's no such thing as a molecule of sodium chloride or magnesium chloride. Those are the formula units. So ionic and compounds and molecular molecules are a little different. Molecular compounds tend to have relatively lower melting points and lower boiling points than ionic compounds, and many molecular compounds will be gases or liquids at room temperature, in contrast to those ionic compounds that we talked about, which are formed from a metal combined with a non-metal. Most molecular compounds are composed of atoms or two or more non-metals, so a little bit of a difference there. Water, which is a molecular compound, and sodium chloride, which is an ionic compound, are compared here. So we have the collection of water molecules. We have one molecule of water, and then the chemical formula, H2O, which is a little off there. For sodium chloride, here we see the array of sodium ions and chloride ions, the formula unit of sodium chloride, and then the chemical formula is NaCl. So comparing the two there. So that's the end of this first section in chapter 8. We will see you for section 2 soon. Take care.